right, babies and gents, put on your happy pants because we're making some boost. That's right, we've gone from proof of concept to let's see how much power we can make. Towards that end, we've increased the boost in 3 phases. You know, before you saw a peak of 2 psi and then it tapered off to like 1.1, I don't exactly remember, but it was kind of sad. But at least it worked and it stayed together. So the next steps were to basically increase the power as much as we can and see what we can actually get out of this setup. Towards that, I can say this: she's gonna fight me for every 1/10 of a pound. But hey, you know what? Didn't a wise man once say, don't look for a place to lose 100 pounds in a race car, look for 100 places to lose 1 pound? Same kind of concept goes here. Except there are 2 major things that we could do that are significant that would up the boost considerably. Having said all that, before I get to those things, that will be at the end of this video, let's look at some little things that we can do. Now, first of all, I had to build a capacitor bank, and what I had here in stock were 63 volt capacitors. And since I've decided to step it up to 16 cells, which I'll get into a little bit later, I needed a new capacitor bank because 16 cells is 67 volts. So these 2 little pretties are 100 volt, 20,000 microfarad capacitors each, and they are going to be the new capacitor bank for the ESC. And the nice thing about them is they're screw terminals. I mean, $56, you'd think they'd include the screws, right? But, you know, this is not junk. It's actually made in the EU, interestingly. But anyway, so we'll use solid copper, 1/8-inch thick copper to fabricate bus bars out of this. That's really not going to do a whole lot to increase boost, but it will allow us to pump more power into this thing. It's worth noting that at this point we have a whopping 8 poles on the setup, and that's without any Loctite on the mechanical fuse bolt. It didn't back out. I think I put the quotes in the wrong spot there. But it didn't back out, so everything seems to be working perfectly, so that's kind of good news. Anyway, so these capacitors will be involved shortly. Now, other things that we can do is, since we are talking about extremely high current draw, even the slightest resistance actually makes a difference in the power draw. Although, as you'll see, our circuit turned out to be pretty tight. But anyway, so this thing, speaking of circuits, this is CircuitWorks. It's a silver conductive grease by Chemtronic. So this wood is pathetic. Like, less than 1/4 of an ounce is $40. But the idea here is every place where there's one of those barrel connectors, you know, we'll put this on the interface, and it should greatly increase the conductivity and therefore the losses. You know, we're looking at something like 2/10 of an ohm resistance for, well, effective circuit resistance as far as the batteries are concerned. So, you know, even 1/100th of an ohm makes a significant difference. So anyway, so having said that, you know, we can put this stuff all over the place. Let's get right back into the car, and we went first from 12 cells half charged, our first test, to 12 cells fully charged. So here are 12 cells fully charged. I'll let you listen to it. You can hear as I roll into the throttle, and then when I hit the button, it sounds like, for all the world, a small shot of nitrous. Check it out. So this one's just a little bit fun, because what you saw there was actually the 3rd pull, or attempted pull, actually. This is the data log overall, so this was the 3rd pull that you just saw here. This was an attempted pull, and I'll get into it later, and this was the 1st pull. So the reason why I did that is because I wanted to, you know, see if you could hit it twice back to back without issues. And when I first opened up this data log, I have to admit I was a bit excited when I saw max 4.8 psi, but then I realized why. And that's because of this mess here. And it's, you know, let me zoom into this. Let's take a look. You can see what's going on. So fundamentally, at this point, I floored the throttle, obviously here. So let's go through the lines again, because I'm still kind of in the same mindset of the last video. So the green line is throttle position. The red line is boost PSI. The white line is RPM, and the yellow line here is air-fuel ratio. On the bottom graph, you basically have a couple of redundant lines plus some additional information, like duty cycle, so that I could approximate horsepower and all kinds of stuff, and spark advance and whatever. But anyway, right now we're just looking at the top map. So you can see that, you know, we hit wide open throttle and we're cruising for a little bit, and, you know, true to form, this thing is showing a 1 psi restriction or equivalent restriction at wide open throttle, just sucking through the blower with it off. But then when I hit the button, it started going up. So the boost started going up. Now here's the problem. So one of the things I noticed about, well, it's not really a problem, it's just an observation. One of the things I noticed about these lithium batteries is that on the first hit, they never perform quite as well as they do on the second hit. And that's because lithium batteries do like to be warm. They do better when they're just a touch warm. They don't want to overheat. You don't want them on fire or anything, but they do tend to put out more power when they're a little bit warm. So the second hit is always better. Now, the reason why this mess happened here, and suddenly, you know, you see RPM just fall down like a, you know, like a cliff, basically, is that this thing has an Afr Safety System. And that part of the map where boost pressure is relatively low, I never really tuned for it, because with the Whipple, it's like all or nothing. You know, even on the trans brake, you're over 13 PSI already, and, you know, you might be seeing 15 PSI peak down track. So it's pretty much a straight line. So again, we're never playing in these relatively small areas. So like here, for example, it's 2.1 PSI, and then we step through it. It goes all the way up to about 2.7 PSI. And what's happening, the reason why the Afr safety system kicked in is that, again, relatively low boost levels. And if I take this section here and look down here for the averages, our air-fuel ratio is actually kind of lean. It bounced between 12.4 and 13.1, and for an average of 12.79. So the deal here is, if the computer senses a lean condition under boost of any sort, I went ahead and changed that later and we fixed that problem. But under boost of any sort, and it's leaner than a 12.5 for, I think, a period of half a second, it will kill spark, and then ultimately, if the RPMs don't drop, it'll kill fuel. So it's actually a pretty cool system. But again, this area was just not tuned. But the interesting thing is, obviously, it took me, you know, how long did it take me? What kind of reaction times the old man got? Let's take a look. 0.322 seconds. So less than a third of a second to figure out what was going on and get my finger off the go button. So, you know, everything then dropped, and basically what happened is, you know, it was just basically pushing air into an engine that wasn't really consuming any. So the boost spiked, and over that lovely little stretch, our boost average is 3.9 pounds. That's pretty good. Peak of 4.8, but of course the motor's off, so what difference does it make? Anyway, so let's bounce back to looking at the pull that you just saw. And that was literally like right after that little fiasco over here. So time-wise, you know, from the time I lifted to the time I got back on it was about 2 seconds. So, you know, didn't give them much of a chance to rest. So this is a good proof of durability and everything else. So again, green line is throttle position, red line is boost, or in this case restriction, and still true to form, we're right around negative 1.1 pounds restriction before we hit the button. But then we hit the button, and then good things happen. And you saw I slowed down the hit speed, so it's less stress on the bolt on the impeller. And looks like we got up to speed in about 0.9 seconds. That may be a touch long if you count this little leveled off area, but you know, generally I've been seeing about 0.75 to 0.8 something. So, you know, it's a good speed. It's a good amount of time to ramp in where I feel it's safe with the bolt. Anyway, so once it did get up to speed, you can see the RPM went up thanks to the converter slipping. Why? Because there's more power and more load on it, which is always a good sign. And we saw a peak boost of 2.4 psi, and it went down to, and this is at about just under 5,000 RPM, it went down to 1.6. So there you have it, 2.4 versus 2.0 and 1.6 versus 1.1. Again, I think that's what it was. So, you know, we saw some improvement. That's just by charging the batteries that were there. And then our next test was going from those 12 cells to 15 cells fully charged plus 4-gauge welding cable instead of the 6-gauge welding cable for power wires. With the 15 cell pull test, we actually didn't just add the other 3 cells to the 12 cell deal. We also changed the power cables from 6 gauge. Remember, we're running about 8.5 feet of 6 gauge cable to 4 gauge cable. I also got smart and decided to put some instrumentation in the car too. So the green digits you see down by the shifter is the ammeter, and then small and possibly not real visible for you guys is the voltmeter. That's the small red digits, and just below that in blue is a thermometer, which is right now just sitting in the passenger side footwell. Eventually it'll probably go on the ESC or something, so I can keep tabs of that. But I'm actually feeling pretty good about the cooling issues, or lack thereof. I mean, frankly, when you're in boost, the car is moving and there's a ton of air flowing through that stuff. So you know, it's actually proving to be a pretty good setup. So again, you'll hear me do the same thing, and that is I'll go wide open throttle, and then a second or so later I will hit the button. Check it out. So here's the data log, and this is another double, actually. That was the second pull, and the reason why it's another double is because, frankly, I just forgot to start the camera. But again, we noticed the same trend as before. As the batteries warmed up after the first pull, a little bit later, they performed better. And you know what? 15 cells really did make one heck of a difference. These are still the 6,000 milliamp hour batteries from Z, which are proving to be fantastic. They don't have as high of a C rating as the bigger batteries we got from Z, but they're still proving to be pretty darn good, especially in that initial burst. They do drop off more just simply because of capacity and voltage drop issues. But they do push the motor basically to its max on initial hit anyway. Although we did a little bit better. So this is where I was wide open throttle. It's pretty straightforward. Again, the classic 1 pound of boost. Classic, that's hilarious. It's only like the 4th pull. 1 pound of boost restriction. And then from here, when we hit the button, again, green is throttle position, so it's been floored for a minute. And then red is boost, and white is RPM. And by the way, I fixed that funky area in the map, so now everything is nice and clean. And these are actually some really clean traces. I'm pretty pleased with how these things look. There's not a whole lot of bouncing around and just oddball points. It's actually really smooth, so this is looking pretty good. But anyway, so this time to accelerate, it took 0.8 seconds. So just over 3/4 of a second. Probably let's call it 3/4 of a second because I may be a little bit pregnant on my line there. So peak boost here on this pull was 3.8 pounds. So we're at 3.8 PSI, ladies and gentlemen. Thank you. We are at 3.8 PSI. It's almost 4 PSI. That is starting to talk some power. So we're looking pretty good. You saw the current. It went from, it hit 280. Now, one thing I need to say about this ammeter is it updates about half as quickly as the other meter. I was going to say half as slowly. I had to think that through for a second. So it's going to miss the absolute peak, or being closer to the absolute peak like the other meter caught. So this one saw 280 amps. I'm sorry. So this one saw 280 peak amps, and it dropped off over the duration of the pull. And of course, let's take a look. So the duration of the pull itself was about 3.2 seconds. So over 3.2 seconds, it dropped from that initial hit of 280 down to 230 something. So there you have it. Voltage-wise, it was right around 48 and change, 48.8 it kind of looks like. It's a little hard for me to tell even. And I'm looking at this on a giant screen in the original video file. But that seems to be about the ballpark. So we're looking pretty good. I think we're actually making some decent boost. And by the way, we maxed out at 5,072 RPM. We're pushing against the converter pretty good. Life is great. Let's move on to the next test. And finally, I'm really, really jazzed to report that the battery company that manufactured the batteries that we bought at the beginning, this company Z, there's 3 E's in that. Anyway, we were looking at, they have these new kind of gigantic batteries. They're actually 9,000 milliamp hour 4S packs, and they fit perfectly in the box that we made and everything else. And of course, it's 50% more capacity with a higher discharge rate. These are, I believe, 100C batteries. But they're in the car right now because, you know, that's That was the last trick. So it went from 15S and 6,000 milliamp hour cells to 16S and 9,000 milliamp hour cells. Now that did make a difference, but the biggest difference it made was not so much in peak boost, but average boost and how well the boost hung on through the pull. So let's take a look. Here with the super awesome batteries that Z sent us, were 16S, 9,000 milliamp hour batteries. So 50% more capacity, a higher discharge rate, I believe. I forgot what the other ones were off the top of my head. But just more power and more power to carry it through. So let's check this one out. So there you saw a peak of 284 amps, so 4 amps over the 15S smaller batteries. But the big news is that it carried it through better. So it never went down below, what was it, 247, whereas on 15S it dropped down to 239. So we're doing really well. And of course our boost level here peaks at 3.9 pounds. It carried it out much better. And if we compare it with the other, let me pop back to the other graph, which I believe is still here. Here it is. So this one, if I look over its sort of best section of pull during the duration of the entire pull, our average boost was just over 3 pounds, 3.08 psi. So 3.08 psi. Okay, well we're starting to get somewhere, fellas. So let's go back to the 16S graph, and so that would be this one. They look frighteningly similar because it's dead nuts repeatable, which is also great news. So with the 16S cells, over approximately a very similar period, we're at 3.33. So basically 3 1/3 psi on average over the duration of the pull. And we are, and our maximum, by the way, is 3.9 and our minimum is 2.7. Whereas with the 15S pull, our maximum was 3.8, but our minimum was 2.4. So there's a significant difference there. So we're looking really good. Let's get back to the other desk and see how we can make even more power. So there we are. We're doing pretty good, I think. Looking at the duty cycles, one thing I didn't really talk about when I had the graphs up, but you can go back and check it out. But basically, the duty cycles don't really increase a whole lot. It's maybe 1 or 2% over the duration of the pull. So that tells me that when we get this thing on the dyno, you're basically looking at a horsepower line. The bigger variation, I think, is going to be the slippage of the converter, frankly. And if I was to guess, as we go up in RPM, the converter slippage will go down, so we should see a rising horsepower curve. But if you've ever dynoed a power glide, they can be a bit of a challenge. Anyway, having said all that, that's still a couple videos away. The one thing we really need, the biggest thing we could possibly do, is get an SI impeller. One thing I want you guys to keep in mind is that this is not some, 2-liter 4-cylinder. This is a 565 cubic inch V8 Ford. Although I think the lifters and the lifter guides are the only thing Ford about it. It's a Dart Iron Eagle Sportsman block. Yes, there is such a thing. It falls between SHP and Iron Eagle, and how I ended up with that specific block is kind of a long, weird story with a machinist with tentacle eyes. It's just kind of weird. We'll just maybe some other time when it's story time. Get the pellet stove going, we can talk about tentacle eyes. Anyway, so that's how I ended up with that block. The heads are, the old school twisted wedge 170s, but they have had pretty heavy porting work. They're opened up to 184, 185 cc's. They've made 3 trips to the flow bench, so they flow a genuine 292 CFM. Basically, what you're looking at is what would be considered fairly modest 6-liter LS for comparison that everybody might know these days. I have to say the LS3 would probably be, with a cam, would probably be a little bit stronger. We're only running 8.8 to 1 compression too, and plus those LS heads are just amazing heads. They flow a ton. So anyway, we are talking about something that makes some power, and this thing makes about 500 horsepower at the flywheel. I say about because the last time it was on the chassis dyno, it pulled about 363 rear wheel horsepower naturally aspirated. Again, that's through a glide, and using the fuel consumption, the duty cycle calculation versus brake specific fuel consumption, you're looking at about 480 flywheel horsepower ish. And then, you know, since then we've added the long tube headers, which probably contributed more torque down low than horsepower up high, but give it a few for that. So, you know, plus the thing is remarkably quiet too. And so is the blower. Haven't heard it. Anyway, I keep diverging, or I keep digressing from the big thing. We need an SI impeller. That is, the impeller we have right now is an SC trim impeller, which is probably the worst choice for, you know, in this style, size of blower. It's probably the worst choice because the SC was actually designed for the Mustang Cobras, the 4-cam deals, which revved high, so they expected people to spin these blowers harder. So what they literally did is they turned down the outside of the impeller fins, so everything has to shift up 5,000 RPM, and since we're playing down near the bottom of the compressor map, you know, we need something that's really efficient, and the SI impeller is a sweet piece. So if anybody has one, anybody knows where they can get one, leave it, just leave a comment down below and I'll let you know how to get a hold of me, and hopefully we can set something up and work something out. A volute will be nice too, but realistically I think I could machine the one I have. I have a boring head for my mini mill, and we're talking about taking it out concentrically 1/10 of an inch. So it's 50 thou on a side. That's really not a whole lot, and we should be able to do that with pretty decent precision. Plus, I don't think it's going to affect the curvature of the impeller, but I could be wrong. But because I don't know if there's a significant difference, but I do know that they machine these housings to fit those. So that would be the biggest thing we could do, hands down. So, you know, hopefully that comes to fruition. My dreams come true. And then the next thing we could do is obviously step up to a bigger motor, because it's clear we're not hitting 50,000 RPM. I do not have the RPM sensor on there yet because it's kind of difficult to put in the car. We will have it on at least when we dyno the thing, but right now honestly we're looking like we're spinning about 28,000 RPM, which I alluded to in another video early on, or I alluded to this situation, and it turns out I think I was wrong where I said the blower was hitting choke and that's why it can't go any higher. There's some other voodoo at play here, which I'm not really sure what it is. If you have some theories, you know, feel free to mention it down below. But that seems to be where we're at. So keeping in mind the power level that we're talking about, even if we somehow manage to hit 7 psi, that should in theory be 750 horsepower. And if you look at like the dyno videos that Cletus, who's now my good friend Cletus, because frankly he's responsible for launching the interest in this particular thing and actually making me go in this direction. I'm having fun doing it, so I'm kind of thankful to him for that. But his dyno videos show actually a really, really close correlation between pressure ratio and horsepower relative to where he started. So if we follow that basic concept, we're doing some like racer bench racing here, but we'll see how accurate it is, because we do have the numbers and the data to make at least an honest, educated guess. Anyway, make a long story short, if we see 7.5 psi, we should see darn close to 750 flywheel at the crank, which is going to put us dangerously close down to the bottom 10s, maybe even the high 9s at that point. But we'll have to see how it all plays out. There may need to be a gear change or whatever to make this thing work better, but we'll find out when we get that thing on the dyno and see where the performance actually is. So a bigger motor is an option. They do make one. It caps out at 40,000 RPM. I would get one with a lower kV, that is RPM per volt, because that effectively gives you less peak speed, since we're not getting anywhere close to 50,000 of this current motor or even the 40,000 of the one I'm looking at. You get more torque. So that may buy us another couple thousand RPM. But the bigger thing, I think, is going to be the impeller. Are you guys getting a hint yet? Impeller. Need impeller. Anyway, so the next thing we could do down the list is port the compressor housing, clean it up, do what we can for flow. I have some experience with that at this point. Not porting compressor housing specifically, but sort of being an airflow whisperer, because I did the intake manifold, which we took 11 pounds out of, as well as the heads. And that was like a lifetime's work. It was forever. But you know, situations dictated that, you know, I'd be hanging around the house. At that time, my daughter was little, didn't want to, you know, obviously leave her alone. So what's a man to do in the evenings but spend some time getting shavings in his socks? I'm never doing that again. It took forever, literally about 100 hours, which is about how long that story took. So anyway, so you know, I feel pretty confident that we could port that compressor housing as well as machine it. So that's basically it. We do have quite a bright future ahead of us, and you know, I'm glad that we're at this point where, you know, let's make some boost, man. Let's make some horsepower. Subscribe.